Hello, this clip's about acids, bases and salts, and before we go into the nuts and bolts of this topic, there's some essential information you just have to know, which I'm going to bring up on the screen. When it's brought up on the screen, you need to pause and make sure you go away and memorize it, because without this information you will find acids, bases and salts very difficult to understand. Once you know the information, then it'll be easy, it'll fall into place, and it'll cease to be a trouble or problem for you. So the first thing to do would be to grab a piece of paper and copy these down, and then go away and boot camp them. In other words, copy them down, read them, memorize them, cover it up, rewrite it, check, and then repeat it as many times as you need to until you're able to repeat this screen off by heart without even thinking about it. What you're seeing on the screen right now is your basic tools that you need in your mind to deal with any acids, bases and salts A-level question that you'll come across. If you don't know this information, you are going to struggle with acids, bases and salts. I can't make it more clear than that. I know I sound like I'm maybe being a bit dramatic, but the number of people who get confused and worried about acids, bases and salts, and when you dig right down under it, what's happened is they haven't gone and memorized this. So a little bit of memorizing perhaps now is what's called for. Take half an hour and just go and get it sorted. Then come back to the video and we'll start getting into the details. Okay, see you soon. Okay, welcome back. I'm assuming you've gone away and revised this, so I'm not going to make reference to it again. The rest of this video is going to assume that you have all this to hand at the tip of your fingers. Okay, so let's now have a look at what acids and bases actually are, what goes on as well. So now it's time to dig out your flashcards for each of these definitions and make sure there's a hand, because I'll also be assuming that you're fully au fait with all of these. So let's take a moment to have a look at the difference between acids, bases and alkalis. In particular, I want to have a look at bases and alkalis, because sometimes these two things are confused. They're interconnected with each other in the wrong way. The key thing to look at here is the fact that it has, under the definition for an alkali, it says it's a type of base. So this means we can consider it, basically, so to speak, in a Venn diagram like this. So this allows us to come to a simple conclusion that will prevent any further confusion later on. So it's one to keep note of for future reference. So therefore, alkalis only produce OH- ions. Bases actually neutralize an acid. So other things can also be bases other than OH-. So there's a few examples to have a think about. CO3 2- is obviously a carbonate, but a metal carbonate. So perhaps I should maybe change that to metal carbonate. So hopefully that clarifies that a little bit. So now what we need to do is have a look a bit more at what these things do when they react with each other. So let's start with an example of something you may have done at school. You might have done this using a test tube, putting some zinc and some sulfuric acid in there, and then using a lighter splint to test for the hydrogen given off. You may have had it demonstrated like this, or even maybe done it yourself like this, as in the picture. So what I've done is I've tried to move a GCSE practical up to A level, and you'll notice in the third question they'll quite often put in a mole question of some kind. So mole questions could appear at any point in an exam. It doesn't necessarily have to be a moles question as such. It might be within an acids and bases question. So to do this, you need to be able to remember the acids and bases reactions that you memorized earlier. So you need to think about what is actually produced when a metal reacts with an acid, and see that there's two marks. It's quite interesting, isn't it? Look at the mark allocation. And the biggest piece of advice of all include state symbols. The number of people who forget to do this and then wonder why they get half marks is quite staggering, really. So make sure you're not one of them, basically, is the advice at this point. So let's pop that in there. What I suggest you do is you pause the video and you copy this set of questions down, leave a space in between each question, obviously, to try and answer it, and have a go yourself, and then come back and see how you did. So have a quick check of what you got. Should be something along these lines here. So what we want to do now is maybe have a look at an exam question from an A-level paper. So I will just pause and open a new slide so we can do that. So this is actually a hybrid of two different exam questions, because you tend to find the theory side of acids and bases dealt with as part A of a bigger question, such as a mole question or a reduction oxidation question. So I've taken two separate sections from two separate papers and put them together so you can see the different ways in which they might ask you. So it requires you to know about all of the definitions from the beginning of the clip, and it also requires you to know a little bit about oxidation numbers, because that's what the V stands for in brackets in phosphoric 5 acid. When we get to that one, I'll explain a little bit about that, but if you haven't watched my video on reduction and oxidation yet, you might want to do that after this if you're not sure. Okay, so it says explain why zinc is a salt. So we need to go back to our definition of a salt, knowing what we know. And I've just realised that I forgot to put in explain why zinc chloride is a salt, because zinc itself is a metal, so the eagle-eyed amongst you might have spotted that. Apologies. So that's how it should read. Explain why zinc chloride is a salt. So obviously it's because zinc has replaced H plus in hydrochloric acid. Then it says predict the formula of the zinc salt that could be formed by adding an excess of zinc to phosphoric acid. So this 5 here refers to an oxidation number. So if we think about the elements that are present in phosphoric acid, the hydrogen is going to be +1, as always. The oxygen is going to be -2, as always. So the V stands for 5 in Roman numerals, which is going to be the oxidation number of the phosphorus. So although it's slightly outside of acids and bases, it's worth just remembering that that's what that means. So, looking at the acid, what's going to happen? The hydrogen is going to be released as H+, so you're going to have 3 lots of H+ released. Therefore, what you'll have left is the PO4- ion. So, if we've got the phosphate 5 ion as PO4-3-, having taken away 3 lots of H+, we can work out that zinc has a charge of 2+. How can we work that out? Zinc chloride. So chloride ions are -1. That gives us a charge of -2 overall from the chlorine. So therefore zinc must be 2+. So if we're working with zinc being 2+, we need to make sure that our compound, our salt, has an overall charge of 0. So we've got to balance the charges up. So this is what we come up with. So if you need to pause for a moment to have a think about why this is, please do so. I'm actually not going to explain it, because you need to do a little bit of thinking yourself as well. So what I am going to do is go on to calcium oxide underneath. So the key thing here is to actually look at what they're reacting it with. It reacts with water, it reacts with nitric acid. And if we think about what calcium actually is, calcium oxide, you've essentially got these two things going on. So it's basically requiring you to remember the equations we looked at before, isn't it? So let's now look at what they want us to do. They want us to predict the formula of the compound, not do an equation, just to predict the formula. So these are the compounds that we're after. Now, how did I know it was actually calcium nitrate? It's because calcium is the metal and nitric acid is the acid. Calcium nitrate is your salt. How did I know it's 2 lots of nitrate? Well, that comes from knowing the charges on your ions. Now, you must know the charges on your ions. There's no way around it. You just have to go and learn them. I said it like that because so many people try and skate around doing that because for whatever reason they don't feel like learning a list of ions. This is where that comes unstuck. So this shows you that the list of ions is absolutely essential. So seeing as we're talking about ions, I'm going to spend a couple of minutes going through how to do an ionic equation, because an ionic equation is part and parcel quite often of doing acid-base reactions. So it's time for a new slide now. So all an ionic equation is a way of representing the reaction, but just looking at the ions that are reacting with each other. It can be applied to a number of different types of reactions, including acid-base reactions. So let's have a look at an acid-base example first, and I'll take you through the technique. So taking this example of an acid-base reaction we looked at earlier, the first thing to do is to separate out everything that's aqueous into its constituent ions. Okay, so you might be wondering what all that stuff is. If we take pencil and we do this and this, you can see that the lithium hydroxide splits into 2 Li plus and 2 OH minus. The H2SO4 splits into 2 H pluses and 1 SO4 minus. The Li2SO4 splits into 2 Li pluses and 1 SO4, 2 minuses. And the water is left the way it is, as a liquid. So what we do now is we cancel out anything that occurs on both sides. So if we take our pen again, there are 2 lots of lithium on both sides. There's a sulfate on both sides, so that leaves us with 2 OH, 2 H plus on the left side and 2 H2O on the right hand side. So that gives us H plus OH minus turning to H2O liquid, which is the exact reaction that takes place in every single neutralization. It doesn't really matter which acid-base reaction you choose, that's what essentially happens if it's a strong alkali and a strong acid. So here's a little diagram that might help you visualize it a little bit, using some other examples of salts, bases and acids. So we can also apply this to simple displacement and also redox reactions. So let's look at a displacement example. So I'm going to let you have a go at this one. Pause the video, see if you can do this, and I'm going to give you a couple of minutes, then you can come back and check. Okay, did you come up with this? Hopefully you did. I'm going to do a slightly more advanced version. I'm going to stick with this reaction. This time I'm going to switch away from acids and bases and move on towards redox. So you'll see that I'm jumping from one topic to another, and that's for the more advanced students. So people who are trying to push for A's and B's need to have that level of flexibility in their minds. So in the bottom right hand corner, what we're going to do is use the Cu2 plus example, but this time I'm going to ask you to think about, is this a reduction and oxidation reaction, and if so, use oxidation numbers to prove. So if you're not sure what to do on that, make sure you've had a look at redox in your book, and maybe had a look at my video on redox reactions before you start. So the first thing to do is to assign oxidation numbers to as many things as you can, which I'm about to do. So the next thing I need to do is check what's been oxidized and what's been reduced. So what's changed in oxidation number? Let's start with copper. Copper has gone from +2 to 0. Has sulfur changed? No, it's +6 on both sides. Has oxygen changed? No, it's -2 on both sides. But magnesium has gone from 0 to +2. So that means that if copper has gone from +2 to 0, it's dropped in oxidation number, so it's been reduced. And if magnesium has increased in oxidation number from 0 to +2, it's been oxidized. So now we need to just put that into words underneath. Okay, I just thought I'd do that while we're talking about a displacement reaction, take advantage of the situation and do a little bit of oxidation and reduction, because it's something that many people struggle with. So to drop it in, perhaps out of context, is quite good. So it makes people think about it in different contexts, not just in reduction and oxidation. So it shows you that reduction can occur anywhere, not just in specific redox reactions. It can occur in other types of reactions too. So in other words, this is a displacement, but it's also a redox reaction as well. Okay, quite a lot covered this time, so please feel free to rewind and have another look, come back another time and have a look at it, or take some of the ideas to your teacher, which are subject extensions, and thanks for listening. All the best. Bye.